Static electricity is a phenomenon that most of us have experienced, and it can be annoying or mildly amusing, but it has the potential to lead to something catastrophic. In the home, static electricity is seldom dangerous, but in industrial environments where flammable and explosive atmospheres are present, its presence can have serious consequences. Let's look at the fire triangle. In order to create a fire or explosion, three things are required: a fuel source, oxygen, and a source of ignition. If these are present at the same time and in the right proportions, the result can be devastating. Due to the flammable nature of many products handled throughout industry, static electricity is as significant a hazard as any other source of ignition. Although safe operating procedures are designed to control the risks of a fire or explosion, an understanding of what static electricity is, how it occurs, and how it behaves are important. This video will help your understanding of static electricity and help ensure it does not lead to a serious incident. Static electricity is created when friction occurs, as dissimilar materials come into contact with one another. When this happens, one accumulates a positive charge and the other a negative charge. When the materials separate, an electrostatic discharge can occur as the charges equalize. This discharge can result in a spark. A typical example of this is when liquid is flowing through a pipe. The potential for electrostatic charge buildup rises where there is greater physical movement, in this instance where flow rates increase, or through the introduction of something like a fine mesh filter into the line. If the charged liquid then enters a container, such as a tank or vehicle compartment, it will create a charge of opposite polarity on the inside surface. If the container isn't earthed, this in turn leads to the corresponding opposite charge on the outside of the container, which is ready to be electrostatically discharged when the conditions are right. If that happens in an area where flammable gases are present, the consequences have the potential to be catastrophic. So, in summary, the electrostatic discharge is a three-stage process. 1. An electrostatic charge is generated. 2. The charge can accumulate to produce an electric field with high strength and potential. 3. The high field strength leads to the electrical breakdown of an insulating material, usually air. It's important to understand this process, as we'll see later. Within industry, the conditions for static electricity to occur are many and varied. Static may be created when water settles through oil, or when liquids are being stripped or blown. It may occur when solids or powders dissolve in a liquid. The flow of material when grip blasting can leave the hose nozzle and blasting equipment highly charged. Wet gases such as steam and high-pressure water can also generate very high levels of static electricity, for example, when there's flow through composite materials. Even a nylon rope passed through a gloved hand, or the removal of clothing, can create static electricity. There are various ways to mitigate the risk. In an industrial environment, by far the most effective method is through the application of earthing, which will prevent the most common problem, accumulation of charge on a conductor, and the release of that energy as a single spark to earth or ground or to another conductor. Earthing reduces the static electricity hazard, but it's important to be aware that it may not eliminate it completely. Let's look at an example, in this case, a conductive storage tank. If properly earthed, the charge on the outside of the tank will flow to earth. But a charge can exist in the tank for some considerable time following pumping or mixing. If a metal sampler or dip tape is brought close to the liquid surface, this charge will rapidly discharge, leading to a spark. If a container hasn't been correctly earthed, bringing a conductive object close to it, such as a spanner, or even touching the container with your hand, could cause a spark. Should this occur in a flammable or explosive atmosphere, where fuel and oxygen are present and in the right concentrations, this sudden electrostatic discharge can lead to a spark, completing the fire triangle and leading to a fire, or even worse. Some materials are better conductors of electricity than others. Conductivity is important because it influences how long any accumulated electrostatic charge will be retained before it dissipates to leave the material electrically neutral. The higher the conductivity, the easier it is to remove the charge. Materials are generally classified into low, medium, and high conductivity. Examples of low-conductivity materials include lubricating oils. Water is an example of a high-conductivity material. There are also non-conductive materials, which are most common plastics, as well as dissipative materials, such as steel or copper. The time taken for a charge to dissipate from a material, and hence the spark hazard to be eliminated, is called the relaxation time. This time can range from a few minutes in a road or rail car and up to an hour in a bulk storage tank. Products with low conductivity and hence the ability to retain an electrical charge pose the greatest risk. A flammable material, usually a liquid or a gas, is one which only requires oxygen and a simple ignition source, like a static discharge, to make it burn. Liquids themselves don't burn. They first have to be converted to a vapor. The temperature at which a substance will produce enough vapor for it to ignite is known as its flash point, and the flash point varies from substance to substance. Of course, this means that some products are more hazardous than others, but as switching products between containers is a common occurrence, all flammable products should be treated with the same degree of caution. For example, a product such as diesel poses little risk in itself, but when being switch-loaded with gasoline, it's probable that the vapor in the container will pass through a hazardous phase. From what you've seen so far, it should be obvious that there are many activities where static electricity could present a hazard. Although it's not possible to cover them all in detail within this video, let's look at a few examples to illustrate the principles of safe operation. Of course, with the move to more automated systems, many of the decisions relating to safe operation are predetermined and out with the control of the operator. But even when a system is largely automated, it's still important to understand the principles behind it and the control measures in place to minimize the risk. A basic control measure when working in environments where flammable atmospheres may be present is the wearing of anti-static dissipative PPE, including footwear, which greatly reduces the risk of operatives themselves generating a static charge. When conducting bunkering operations on process plant or when top-loading road or rail cars, in addition to the container being earthed, the fill pipe should also be bonded electrically to earth, with all the assembly bonded so as to be electrically continuous. The fill pipe should extend to the bottom of the tank and preferably also touch the side. Irrespective of the product, splash filling should be avoided as this increases the possibility of generating static. Flow rates are extremely important in minimizing the buildup of electrostatic charge. Initial flow rate should be restricted until the filling nozzle or inlet has been covered. The maximum flow rate should also be observed. These are dependent on factors such as the conductivity of the product and the diameter of the fill pipe. We've already seen that gauging and sampling have the potential to induce a static discharge. Product under a coned roof tank must be under an inert gas blanket when pumping or mixing is taking place. No conducting objects such as gauge tapes or sample containers should be lowered into the tank until after the specified relaxation time. Even after this period, the gauges should touch earth prior to operation, and the gauging tape should remain in contact with the side of the dip hatch. When taking samples, natural fiber rope should be used to lower the container. Non-conducting synthetic material like nylon must not be used for this purpose. Many of the principles we've covered apply for operations such as drum filling, ship and barge loading, service station operations, and aircraft fuel handling. But you need to be aware that some activities may also have unique products or operational characteristics. Even the seemingly innocuous task of filling a small container has the potential to generate a static spark with potential ignition if the correct procedures aren't followed. Size, type of material, and filling method are all important factors. Most incidents involving static electricity are caused by a failure to comply with correct operating procedures, and a lack of awareness and understanding of the hazards of static electricity may be partly responsible. Although we've mainly concentrated on product movement, due to the high risk, it's important to be aware that other activities are no less important. Maintenance work, for instance, which is relevant in 3 areas. Firstly, as we've seen, some activities can generate considerable static charges. In a flammable atmosphere, these could be extremely hazardous. highlighting the need to comply with the permit to work system, carry out robust risk assessments, and apply control measures to mitigate risk. Secondly, the use of tools in the completion of maintenance activities may introduce risk through incorrect use and inappropriate selection. The use of portable electronic equipment is becoming more widespread, and equipment which is not designed and certified for use in potentially flammable atmospheres can introduce risks. For example, brush-type electrostatic discharges from areas of insulating materials such as housings. Spark-type electrostatic discharges from charged, isolated, unearthed metal parts or other isolated conducting parts. The third consideration is the maintenance of plant and equipment. For instance, interrupting a conductive path to Earth could take a safe operation to something extremely hazardous. Permit to work, hazardous area controls, robust maintenance schedules, and good working practice are all vital factors in ensuring such occurrences are avoided. Finally, in industry, static electricity presents a real ignition risk, and the procedures and control measures covered in this video show how to reduce that risk. But whatever the task you're carrying out, it's important to follow process, identify the hazards, assess the risk, and implement control measures to mitigate the risk, so that everyone goes home at the end of the working day unharmed. Thanks for watching.